Scott's lecture number 2.
Okay. Good morning, everyone. So, by the way, I realized that these 6 problems that I gave yesterday, 2 of them involve material that I'm only covering today. So sorry about that. They're not being graded anyway. They're just, they're just things to try for fun. Okay. So, I should say I'm extremely grateful to Steve Jordan for yesterday afternoon covering some of the material that I was going to cover today, so that I don't have to, and I can actually get faster to the new stuff. So, okay. So. Plan for today is sort of finish this crash course on the wonderful world of complexity theory, see how quantum computing fits into all of it, and then with that background, we'll be ready to start in on discussing quantum optics. Okay, and where we're going is we talked yesterday about the extended Church-Turing thesis. This sort of extremely bold claim, connecting computation to physics, and of course, today many of us believe it's probably a false claim because quantum mechanics probably falsifies it. This is, the thesis that nature can be efficiently simulated using a classical Turing machine. So, following Steve's terminology, I guess I'll call the thesis that nature can be efficiently simulated by a quantum computer the Church-Turing-Deutsch thesis. And so, so that one, many of us believe, but this original ECT, if Shor's algorithm, as we all know, sort of confronted us with a dilemma, which is that either quantum computing has to be impossible, or else, factoring integers, this particular problem has to be in P, or else the extended Church-Turing thesis has to be false. Okay, and all of them, sort of from some a priori standpoint, sound kind of crazy, but at least one of them has to be true. So, and so the reason why we're going to get into quantum optics later is our goal will be to heighten the tension between quantum mechanics and the ECT even further. Factoring is just one particular problem. Some people even think it might well have a fast classical algorithm also. In which case the fact that it has a quantum algorithm wouldn't be a threat at all to the ECT. Okay, but we're going to try to show that actually quantum mechanics threatens the ECT in much more severe ways as well. Okay, so let's see. So we talked yesterday about the P versus NP problem, about these NP hard and NP complete problems, and of the many reasons to suspect that P is not equal to NP, one of them is that, there are just thousands of problems of practical interest that have been shown to be NP complete. Okay, that look completely different, on their face, but, we know because we can give reductions between them that, in some sense, they're all the same problem. If P were equal to NP, then, it's very hard to understand why an efficient algorithm would not have been discovered for just one of these problems. Each one gives you like a different face, a different way of looking at the difficulty. And to prove P equals NP, it would have sufficed to find an algorithm for any one of these things. And yet, again and again, we find algorithms that sort of just sometimes even if we could improve them a little bit, like we can get an answer that's within 10% of optimal. And if we could we know that if we could get an answer that was within 9% of the optimum, then it would follow that P equals NP. Okay, and yet, in not one of those hundreds of cases do we ever find the algorithm that's within 9% of optimal. Okay, so if P were equal to NP, it's sort of, to me at least, it's hard to explain that state of affairs. You can call, okay, so I've noticed that sometimes, a physicist will use the term like physical argument or physical intuition for anything that turns out to be correct. So, So okay, fine. If you want to, like they'll say, well, someone just argued to me, you know, a week ago, Einstein succeeded in his early career because he relied on physical intuition, but later he was just doing math, and so he was led astray. I said, what you really mean is that the mathematical guesses that he made early in his career turned out to be correct, so you call them physical. But anyway, so all right. So there's these NP-complete problems, and but you know there are and I sort of told you this rule of thumb yesterday that you know most among like combinatorial search problems, optimization problems, almost all of them seem to be NP-complete unless there's some good reason for them not to be. And so, you know, there are some problems where, you know, that look on their face like they're hard, but we actually know that they're in P. Okay, then there are other problems that, as far as we know, they are hard. You know, their best algorithms are some sort of exponential time. Okay, but on the other hand, there do seem to be very strong reasons that prevent them from being NP-complete. Okay, and the most famous problem of that type is the problem of factoring integers. You know, and of course, this is a problem of huge importance both for cryptography and for quantum computing. So, you know, it might be worth spelling out, you know, just what are the reasons why we're almost certain that factoring is not an NP-complete problem. Okay, so the explanation. All right, so I guess, you know, a sort of a physicist way to see the, you know, what makes factoring different from any NP-complete problem that we know about would be the following, right? You take any NP-complete problem like satisfiability, traveling salesman problem, whatever, right? You know, there might be a priori, there might be no solutions that satisfy all the constraints, or there might be one, or there might be a million. You just don't know. Okay, but given any positive integer, you know in advance that it has exactly one prime factorization. Okay, so that uniqueness is a sort of property that we don't know any NP-complete problem to have. Okay, but you know, the fact that that you know in advance that there is a solution and that it's unique. Okay, but why is that such a big deal? Well, the answer involves. I'm sorry. Another animal called co-NP. Co-NP is just the set of all the languages whose complements are in NP. You know, complement being the set of all strings that are not in the language. Okay, so another way of saying it is a problem is in co-NP if and only if there are short witnesses proving no answers. Okay, so you know, so for any NP problem, there's a corresponding co-NP problem, right? So instead of satisfiability, you have unsatisfiability. Okay, instead of traveling salesman, you have, you know, traveling unsalesman or something, right? Or you know, the question is there no tour that satisfies, you know, all of these constraints? Okay, so okay, but you know, why is who cares about this? Is this, you know, well, where it gets more interesting is that now you can talk about the intersection of NP and co-NP. Okay, that's this wedge down here. So those are the problems where there's a short proof either for a yes answer or for a no answer. Okay. And now observe that if we were to phrase factoring as a decision problem, so by saying, look, the problem is, you know, is the ith bit in the prime factorization a 1 or something like that, then that problem would be not only in NP but also in co-NP, right? Doesn't matter if the bit is a 1 or a 0. There's a short proof of that either way, namely to give the prime factorization. Okay, and given that factorization, of course, someone can multiply the numbers for themselves. They can check that, yes, these really are divisors. Furthermore, they can even check that the numbers are prime, because primality is in P. Okay, so the conclusion of this is that the factoring problem is actually not only in NP, but it's in this intersection. It's also in co-NP. Okay, and now we can observe that I think I didn't give this on a homework, but I could have. If there's any problem in this in NP intersect co-NP that is also NP complete, then that would have a very striking consequence. That would mean that NP would equal co-NP. Okay, so these two guys would go like that. Okay, and basically because it would sort of make this equal to this, and by symmetry this becomes equal to this, and they all you can formalize that. Okay, so what that would say, what would it mean for NP to equal co-NP? That would mean that there would always be short proofs of non-existence of solutions for any NP problem. So like given any Boolean formula, if it was unsatisfiable, there would be a short proof of unsatisfiability, right? It wouldn't say that that proof could be found efficiently, but if found, then you could verify that yes, you would be convinced that yes, there are no solutions to this formula, okay, or there are no tours for this traveling salesman, or this Sudoku puzzle is unsolvable, or whatever, okay, and to have these short proofs, okay, it would be not quite as dramatic as P equaling NP, perhaps, because it wouldn't say that we could actually find these proofs, but it would still be very bizarre, right? It seems very unlikely that there should always be a short proof of unsatisfiability. It seems like you should really have to sort of do an exponential checking of all the possibilities to be convinced that there are none of them. So just by a slight sort of extension of the intuition for P not equaling NP, we might be tempted to make the stronger conjecture that NP does not equal co-NP. Okay, now this is a strengthening in the sense that if P equals NP, then certainly P also equals co-NP, so then NP equals co-NP. Okay, the converse is not known. So, no one knows how to get from P not equal to NP to this conjecture. Okay, but it seems like a reasonable thing to believe also. And if you believe this, then factoring cannot be NP complete. Okay, so.
But if you show that, you also show P is not NP.
What? Yeah, but I mean, but look, I mean, that P not equal to NP is sort of like a background assumption to everything, right? We're talking about, right? Because if P equal to NP, then you could say that factoring would be NP complete just because everything in NP would be NP complete because everything would equal P. Yeah.
This is at least as hard as showing that.
Oh, that's certainly true. Yes. Yes. But basically what we can say is that if factoring is NP complete, then this whole hierarchy, the whole way that we think things are sort of comes collapsing anyway. So it's so for this particular problem, there really is a strong theoretical reason why it shouldn't be NP complete, you could say. Now, and this introduces sort of a style of argument that's going to be important to us. Okay, so we can go further. Now that we have this NP and this co-NP, okay, to like a mathematician, you would say, why not go further? And like this one is sort of like saying there exists a solution. This one is sort of like saying for all. Like saying for all solutions, that solution doesn't work. Okay, but you could consider more complicated statements where you would say for every string x, there exists a string y such that some predicate holds of x and y. Okay, where would that sort of problem ever come up? Well, let's take one of the oldest problems in electrical engineering and computer science, the circuit minimization problem. Okay, so I give you like a Boolean circuit, and I ask you to find, a minimum circuit which is equivalent to the original one, which computes the same function as the original one. Okay, so minimizing a logic circuit. Okay, and here you'll notice that this is this is certainly an NP hard problem, you could say, right? But it's not obviously an NP at all because suppose someone claims, okay, there is a small circuit that's equivalent to your original one. Here's a circuit of size at most k. there's still a very hard problem. Namely, how do you prove that this circuit really is equivalent to the original one? So you have, so then you have once someone proposes a small circuit, then you have a further search that you'd have to do, which is there an input on which these two circuits differ? Okay, so there's really two quantifiers going on. You're asking whether does there exist a small circuit such that for every input, this circuit agrees with your original circuit. Okay, so if you want to capture situations like that, then you need actually a larger classes than just NP and co-NP. And so there's this beast called the polynomial hierarchy, or the PH. Okay, and so the way that this works is that the 0th level of this hierarchy is P. The first level is NP and co-NP. Okay, but then there are going to be infinitely many further levels. So the second level of the hierarchy, involves statements with two quantifiers. Statements of this form, and a simpler way to define it is that the second level will consist of NP with NP oracle. Okay, which sounds weird. It's like if you're already NP, why do you need an oracle for yourself? Okay, but what this lets you do, if you're in NP and you have an oracle that lets you solve NP problems, then you can actually evaluate expressions with two quantifiers, like this type up here, which you couldn't do if you were merely NP, right? You can ask, does there exist an X, such that, and then use your NP oracle to answer the question, does there exist a Y that would falsify the statement? Okay, so the second level would also include co-NP with an NP oracle. Okay, and I should point out that it doesn't matter whether the oracle itself is NP or co-NP, because once you've called the oracle, you can always just reverse whatever answer it gives you. And so NP and co-NP are like the same thing. Okay, but then like for the final output, you're talking about constrained, where the NP involves a fundamental asymmetry between yes and no. Okay, and okay, so then the third level of this hierarchy would involve, would consist of NP to the NP to the NP. So NP with an oracle for the second level of the polynomial hierarchy, in other words. Okay, or co-NP with an oracle for the second level. And you can keep going this way. Okay, so this would let you, in these classes, you can evaluate statements involving 3 alternating quantifiers. And then you could have 4 quantifiers and so forth. And then the polynomial hierarchy is just the union of all of these over every finite, every fixed number of quantifiers. Okay, so it's the so it's that entire hierarchy, and then this automatically includes all the co-NP ones also, because co-NP is certainly going to be an NP to the NP, and this one will be contained in that one, and so forth. Okay, so yeah. What? Oh, well, I just explained that, right? Because if you have a co-NP oracle, that's just the same thing as having an NP oracle, because you can after making the oracle query, you can just reverse the answer, right? So it's just the final output where there's this asymmetry that you can't get rid of. Okay. Okay. So no, actually, you could even wonder, what if we allow, a number of quantifiers that grows with the size of the input? You could even imagine having a polynomial number of quantifiers. So for all x1, there exists an x2, such that for all x3, and so forth. Now, where would a situation like this ever arise in practice? I'll tell you where it would arise. If you're trying to play a game like chess or Go, okay, I don't know if that's practice, but this is where it would arise in recreation. Okay, you have like a two-player game with alternating moves, right? An expression like this is just saying, like, does there exist a winning strategy for player one? So, like, does there exist a move that player one could make such that for every possible response of player two, there exists a response of player one, such that for every response of player two, and so forth. And then you would have some polynomial time algorithm that at the end of the day evaluates which player has won or whether it's a tie.
Where the board size is the
Oh, yeah. Okay. I should have said that. Chess with an 8x8 board is trivial. It's solvable in O of 1 time. Okay. So to even get started in discussing these matters, we have to assume that you take your favorite game and you generalize it to a board of size n by n. So then we can discuss asymptotics. For Go, that's actually very easy to do. Like the choice of a 19 by 19 board is kind of arbitrary. You could have played it with a board of any size. Okay, for chess, you have to suitably generalize it and say, look, you get, more pawns, you get more knights, whatever. Yeah?
So when you say you have an NP oracle,
Yeah.
you don't mean that it provides witnesses on demand. You mean it solves the problem on demand and tells you the answer and you believe it.
Yeah, it tells you whether the answer is yes or no. However, by the homework problem, if you have such an oracle, then you can also use it to find solutions to any NP. You can use it to find a witness to any NP problem where the answer is yes. If you have such an oracle.
But if you have the oracle, you can also solve co-NP, right?
Yes, that's right.
Whereas if you just had a witness producing machine, is that enough to solve?
Oh, well, like if you had a machine that produced a witness whenever there was a witness, then this would just be just the same as having an NP oracle. Yeah, that would be. I mean, that would be equally powerful, because then if it didn't produce a witness, then you would know that there wasn't one.
Oh, but
right.
Yeah, you have to know that.
Yeah. But if it produces one whenever there is one, then if it doesn't produce one, then there wasn't one. Okay. All right. So. So something interesting happens at this point, which is that when you consider games, of alternation between two players, like chess or Go, they almost always turn out to be p-space complete. Okay, again, suitably generalized to an n by n board. Okay, so then you make this leap from the polynomial hierarchy up to p-space. So just to give you a picture of where things stand. So the second level of the hierarchy would be NP to the NP, which contains these two guys, co-NP to the NP here, and then there's all these infinitely many higher levels. Then the whole thing is contained in p-space, okay, which is things you can do with polynomial memory, which in turn is contained in exponential time. You could think of p-space as like the limit of the polynomial hierarchy when you have when you allow n alternations. Okay, and games of strategy, two-player alternating games like chess, Go, those two have actually been proved to be p-space complete. With chess, there's a technicality, which is that you have to say that the game ends after a polynomial number of moves, right? If it hasn't ended in some reasonable amount of time, then it's a draw. If you allow chess to continue for exponentially many moves, then it's actually exponential time complete, okay? Which is a striking fact because, if you have an X-complete problem, then again, but by the homework, we can actually prove unconditionally that that problem cannot be solvable in polynomial time. Okay, that's a rare situation. But for p-space complete problems, we don't know how to prove that. Okay. Yeah. 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 So the polynomial hierarchy was invented by Meyer and Stockmeyer in the early 70s. And it was invented by direct analogy with the arithmetic hierarchy from logic, which, people had studied earlier, right? Which was, around since the 30s, I guess. Oh, that was shown, I think, in the early 80s. Yeah. Okay. So, okay. So what is but what is this polynomial hierarchy really good for? Well, I mean, there are, as I said, natural problems like circuit minimization, where we need this hierarchy to really classify them correctly. Okay, but in addition, this polynomial hierarchy turns out to be a very useful yardstick of implausibility. Okay, so it turns out that very, very often, in complexity theory, we can't, I mean, it's very rare that we can unconditionally prove what we want, right? But occasionally we can, like chess of unlimited length is not solvable in polynomial time. Okay, but usually we have to make some assumption. Okay, and it turns out an extremely convenient assumption to make is that the polynomial hierarchy is infinite. Okay, what does that mean? So if you like, we're just making a far-reaching generalization of our original conjecture that P is not equal to NP. Okay, we saw before that if you stick your neck out a little further, it seems plausible to guess that NP is not equal to co-NP. Okay, but then you could go further still, and you could say, look, it likewise seems implausible that NP to the NP would equal co-NP to the NP. Okay, I mean, we're just sort of adding in an NP oracle, but the basic intuition, seems like it should stand. Okay, it seems implausible that NP to the NP to the NP should equal co-NP to the NP to the NP. And it seems plausible. It seems plausible that no two of these classes should be no two of these levels of this hierarchy should be equal to each other. Okay, so one problem that's, I guess, on today's homework is that is to show that if like NP were, if any collapse of this type were to happen, like for example, if P were equal to NP, then the entire polynomial hierarchy would come crashing down to P. Okay, so that would be the worst collapse possible. Okay, if NP were equal to co-NP, then the hierarchy would come crashing down to NP, or equivalently to co-NP. Okay, but not necessarily further than that. That would still be a very bad collapse. Okay, if this conjecture were to fail, then the whole hierarchy would come crashing down to NP to the NP. Okay, so if you get an equality at any point, then all of the higher levels become steamrolled and just become just collapse and become equal. So you get like an infinite tower of conjectures, right? That at each level you believe that these classes are distinct. But this is a very standard. It feels like intuitively a modest extension of believing P is not equal to NP. And turns out that if you believe that, it has lots and lots of consequences for other things. So let me just give, okay, so I guess I already gave you one example, right? That if factoring were NP complete, then the hierarchy would collapse to the first level. In other words, NP would equal co-NP. Okay, here's another example. So one of the other famous problems that seems to lie in this intermediate zone is the graph isomorphism problem. Okay, so this is you've probably heard of this problem. This is the one where I give you two graphs and I ask, are they isomorphic to each other? So, can you permute the vertices of one graph to make it equal to the other graph? Okay, very old, very famous problem, has applications in chemistry and in other areas. The best algorithms that we know for this problem take something like 2 to the square root of n time, where n is the number of vertices. Now, many of us, including me, suspect that this problem may actually just be in P. Okay, why? Because we have algorithms that work very well for the problem in practice. We can't prove that they always work. And, and for many of the algorithms, there are even very bizarre counterexamples that one can construct. Okay, but it's not like, it doesn't feel like factoring, where if you just pick a random large integer, then it's probably quite hard to factor. Okay, graph isomorphism, if you pick graphs randomly, then they're very trivial to distinguish from each other. And in fact, finding graphs that are not isomorphic but that are hard to tell apart is itself a very hard problem. Okay, so this might be in P, but we certainly don't know that. But on the other hand, we do have extremely strong evidence that graph isomorphism is not NP complete. Okay, and once again, the type of evidence that we have is that if graph isomorphism were to be NP complete, then the polynomial hierarchy would collapse to the second level. Okay, so this is a theorem from the 80s, and I could go, and once again, it uses sort of special structural properties of the graph isomorphism problem. In this case, more subtle properties than you use for factoring. For graph isomorphism, it's not true that there's a unique isomorphism, whenever there is one. Okay, but the fact that it's an isomorphism problem gives the problem like a group theoretic structure that ultimately enables you to prove this. Okay, so this is another example of the mileage you can get. If you'll grant this one assumption that the polynomial hierarchy is infinite. Yeah.
So you explained yesterday why P equal to NP would mean we could solve the Riemann hypothesis
Yep.
by
Yep.
searching through the theorem space. I'm having more trouble figuring out what the implications of
Yeah.
collapse to the second level.
Right. Well, it's much more abstract, right? It would say that, like, would basically say, in this world with, like with an NP oracle, right? That that it within that world you would get a collapse, right? Like you might be tempted, once you've convinced yourself of what that P should not equal NP, then it's tempting to say, look, imagine that in the world there were magical boxes that solved NP complete problems. Okay, even relative to those oracles, as we would say, or even in that hypothetical world, right? We could still make up problems that would seem like they should be hard. Okay, namely, we could say, I'm searching for an X such that this box will fail to find a Y, such that phi of XY holds. Okay, and
So, well, you would
yeah,
use the hierarchy in terms of games like
yeah,
chess or Go,
yeah.
where you had a series of quantifiers.
Right.
What would it mean for one of those spaces?
Okay, well, so what it would mean would be that, like, a game, that if you could, for the hierarchy to collapse, let's say the second level, would mean that if someone gave you a magic box for, solving games with 2 moves, then you could also use that box to solve games with 100 moves, for example. Okay. Yeah.
Are there any complete problems for all levels?
Absolutely. Yeah, yes, there are. So every level of the hierarchy has its own complete problems, which as you get higher up, there are fewer and fewer natural complete problems. Right? You can certainly get an artificial, like almost by definition, just get a complete problem for any level of the hierarchy you want. But there are for the second level, and I think even for the third level, there are some natural complete problems, which I forget examples of them. But for the fourth and higher levels, I don't know if we have natural examples. Okay, so yeah, yeah. What? E equals the union of P and NP and NP to the NP and NP to the NP to the NP and so forth. Yeah. Yeah, that's right. That's right. Yeah, yeah. It means that it collapses to the second level. Okay, so yeah.
So is there also an independent conjecture that pH is not distinct?
Yes, that's correct. There is. Now, one thing that we can say is that if pH were equal to p space, then pH would have to collapse to some level. Okay. Why? Because if there were a simulation of p space and pH, then the simulation would have to exist at some level of the pH, right? And whatever level that was, pH would then collapse to that level. Okay. So, all right. So in fact, yeah.
Is it possible to postulate, for instance, that this structure collapses to, let's say, the third level, you find an isomorphism there? Like you're saying that there is a graph that describes the
Yeah,
then you have only NP to the NP.
that's right.
So is it possible to then say for NP to the NP to the NP there is such and such isomorphism?
I don't understand what you're asking. If graph isomorphism is NP complete, then the hierarchy collapses to the second level. Therefore, also it collapses to the third level, and all the.
Is graph isomorphism the most general?
Oh, you're asking, are there, we're going to see later in this course, we're going to see examples where I only know how to give collapses to the third level, if something is true, okay? But, the biggest one I know is that there was someone on this Stack Exchange site asked me a question, can you rule this out? And I could tell them that if it happens, then the hierarchy collapses to the fifth level. Okay. So, okay. So let me just someone asking something. Okay. So let me just give you one more animal that's one that's going to play a very important role in this course. This one is called sharp P. Okay, and sharp P is basically the class of all combinatorial counting problems. Okay, so you could define sharp P by saying, take any NP problem, right? An NP problem is a problem like, does there exist a W that, satisfies, that will make this polynomial time Turing machine happy, right? And then from that, you can get a sharp P problem. The sharp P version would be count the number of W's that cause the machine to accept. Okay, so sharp P is the class of all problems of the form, I give you, there's some polynomial time Turing machine M, and then there's some input X, and now the problem will be to count the number of strings W of some fixed polynomial length such that M accepts given X and W as inputs. Okay. So here, we're asking for something harder than just than just solving an NP complete problem. Okay, certainly if we could solve sharp P problems, then we could also solve NP problems because we would just have to ask: is the number of solutions 0 or is it more than 0, right? Okay, but in asking for a count of the number of good solutions, you're asking for something that might be much harder to get than just deciding whether there is a solution. Okay, and and for essentially I believe for any known NP complete problem, the counting version of it is also sharp P complete. It's an open problem whether there's any NP complete problem whose counting version is not sharp P complete. Okay, but actually, when you get to sharp P, a couple things that are much more interesting and surprising than that happen. So let me tell you what those are because they're going to be important for us. Okay, so I mentioned yesterday this problem of finding a perfect matching in a bipartite graph, right? So in other words, I have n men, n women. I tell you who is willing to date whom, and the question is, can you pair them all off so that everyone is happy? In this case, I guess the way I drew it, it's trivial to do so. Okay, but you can make examples where maybe it's harder. This. Okay, I don't. Is there a matching in that one? Yeah. Okay. Thanks. So, okay, so as I mentioned yesterday, the matching problem turns out to be in P, right? There's, and this is taught in like introductory algorithms courses. There's a very clever way. Well, you can find the perfect matching whenever it exists in deterministic polynomial time. So this is not, an NP complete problem, unless of course P equaled NP. Okay, so, but on the other hand, in 1979, Leslie Valiant discovered something pretty amazing, which is that if I now ask count the number of perfect matchings, then that problem is sharp p-complete. Okay, so just because the decision version, is easy, or just because the search problem is easy, does not at all mean that the counting version also has to be easy. In fact, the counting version of an easy problem can jump all the way up to being sharp p-complete. Okay.
I'm sorry.
Yeah. Yes.
Something I don't get it right. So
Yeah.
the P problem
Yeah.
is to find if there is a solution or not, right?
Yeah, that's right. That's right.
The solution indeed could be NP, for instance.
Well, no. The P problem would be decide whether this graph has a perfect matching or not. Okay, that problem is in P. It turns out that finding a perfect matching whenever it exists can also be done in polynomial time. Okay. However, counting the number of perfect matchings is sharp p-complete.
Why is that?
There's a reason why Valiant won the Turing Award for proving it.
But I can find all the solutions, and once I found them, I can
Well, okay, well, it's going to take you exponential time. How are you going to loop through every possible solution?
Okay,
Yeah, so you can find a solution, right? But then the fact that you found this one solution doesn't mean that there's not another one, right? So then you find that other one, and there may be exponentially many different solutions. And what Valiant found is that to enumerate all of them, is actually just as hard as enumerating the solutions of any combinatorial counting problem whatsoever. Okay, even though finding a solution in this particular case is easy. Okay, that was the surprise. Yeah.
Is this for matching in general graphs?
Yeah, it's also true for I mean, look, if it's sharp p-complete even for the special case of bipartite graphs, then it has to be for general graphs, right? Because a bipartite graph is a graph, right? Okay, and it's certainly in sharp p for whatever graph. Okay, so actually, one thing that we're going to see by the end of this course, we'll actually see most of a proof, a completely independent proof that counting the number of matchings as sharp p-complete. I'll be able to give you an alternative proof that goes through quantum optics, okay, instead of through the combinatorial stuff that Valiant did. Okay, so we'll actually see how we're going to see two different directions of we're going to see a bidirectional connection. We're going to see how we can use the sharp p-completeness of this problem to argue that simulating optical experiments should be hard, and we're going to see how we can use ideas of quantum optical computing, like this KLM scheme, to give an independent proof that this problem is sharp p-complete. Okay, so another way to phrase Valiant's discovery is in terms of a very important function of a matrix, which is called the permanent. Okay. So I might as well bring it onto the stage. So if I give you an n by n matrix, it could be over any field. Let's just say for now that it's a matrix of ones and zeros. Okay, then the permanent is simply this function. So an easy way to define it is that it's just like the determinant except without the minus signs. Okay, so it's the sum over all n factorial permutations of the product of the entries of the matrix along that permutation. Okay, so what is the connection to matchings? Well, very simple. If you take your bipartite graph and you create its adjacency matrix, so you just put like label the rows by the left vertices, label the columns by the right vertices, and then just put a 1 wherever there's an edge between the corresponding vertices, then the permanent will simply be counting the number of perfect matchings for you, right? That's just like by definition, right? It's counting, you'll add a 1 to the permanent, for every time there's a perfect matching in your graph. Okay, so another way to phrase Valiant's result is that computing the permanent, even for a matrix of zeros and ones, is a sharp p-complete problem. Okay. That fact is going to be extremely important for us. Okay, so and there's a very interesting contrast here with the case of the determinant. So to remind you, the determinant is that function there. And the determinant, of course, is computable in polynomial time using Gaussian elimination, for example, or just by finding all the eigenvalues, and then the determinant is their product. Okay, so those methods will find you the determinant of an n by n matrix in n cubed time. In fact, there are even theoretical methods known that will find the determinant of an n by n matrix in n to the 2.373 time. Those are not very practical. But in any case, the determinant is in P. And so despite the similarity of their definition, these two functions are completely different in terms of their computational complexity. Right? This one's in P. This one is sharp P complete. And so you could ask, where does the difference come from? And one way of understanding it is that the determinant just has much more sort of geometric structure, right? It has linear algebra. It has a linear algebraic interpretation, right? The determinant can be interpreted as the volume of the parallelepiped spanned by the rows of the matrix, right? And these things really give you a very good computational handle on the determinant. For the permanent, it has these combinatorial interpretations, like counting number of matchings, but it has no known geometric interpretation. Okay, and there's a good reason why it shouldn't have one, because it's sharp P complete. Okay, if you had such an interpretation, then why wouldn't that show that you could do sharp P in P, right? So in fact, one of the central goals in theoretical computer science since the 1970s has been to really prove rigorously that the permanent is harder to compute than the determinant. Okay, and this is sort of believed by almost everyone to be like an essential warm-up. Like, if you wanted to prove P not equal to NP, then this is the thing that you should do first. Okay, because the permanent and the determinant, it is very closely related, right? You're asking about sharp P and about the determinant is a little maybe doesn't capture the full power of P, but it's it's in there somewhere. Okay, and but both of these functions just have all sorts of beautiful mathematical properties, right? That give you hope that you could just, if you just threw enough yellow books at this problem, that you could maybe prove that the one is harder than the other. So there's this whole program today called Momoli's geometric complexity theory that tries to use algebraic geometry and representation theory to argue that the permanent is harder than the determinant, and and ultimately what he wants to use is that the determinant has just a much larger group of symmetries than the permanent does, right? The determinant is symmetric under like if you multiply, if you were to left multiply or right multiply A by any other matrix, then we can control. We know how that affects the determinant. Okay, whereas the permanent, you start multiplying matrices, and it you have no control over what happens to the permanent. Okay, the only sort of the only natural symmetries that the permanent has are that, well, you can permute the rows of the matrix. That won't change the permanent. You can permute the columns. You can multiply any row or any column by a scalar, and that will multiply the permanent by the same scalar. Okay, so there's a smaller group of symmetries. So the interplay between the relation between these two functions is a fascinating thing for math and computer science. As we're going to see, it's also a fascinating thing for physics because this function is very, very closely linked to fermions and this one to bosons, as we'll get into shortly. Yeah.
You say it's believed to be a warm-up.
Yeah.
Would P equal NP imply that P sharp is P?
That's an excellent question. No such result is known.
So hypothetically, might it
Yeah.
be that the warm-up is the harder one?
Well, okay. Well, wait. certainly if p were equal to p to the sharp p, right? If the determinant could be done, if the permanent could be reduced to the determinant, then certainly p would equal NP, right? So if p were not equal to NP, then certainly the permanent has to be hard. Okay, so in that sense, it is a weaker conjecture. But then people consider the permanent versus determinant over other, like over the complex numbers with circuits that get to natively use, reals and complex numbers, and then it gets more complicated. Okay, but if we just look over, say, the Boolean field, then it is a weaker conjecture. Yeah.
Are there any natural anyonic intermediaries?
So yeah, you can define. All right, so I'm going to get to this later, okay? But you can define, there's a whole class of functions called immanents that generalize both the permanent and the determinant. Now, and which in fact correspond to different types of anyons. Okay. Now, unfortunately, it turns out that almost all of these functions are simply sharp p complete. Okay. So it's sort of like sharp p is just the roof, and you've already hit that roof with bosons. So. So in that sense, it's not that interesting, right? It is interesting for other purposes. But, okay, so that's one, very important fact about sharp p. Okay, now there's going to be one other fact that's that will be important for us. So namely, we'd like to know how does sharp p relate, and this was already, I guess, touched on, but how does sharp p relate to the classes of decision problems that we talked about before. Okay, well, unfortunately, we can't really compare it directly. It's sort of an apples to oranges comparison because sharp p is not a class of languages, right? It's a class where the desired answer is an integer, right? So we can it doesn't even make sense to ask whether it's equal to NP, right? It's like asking, is the set of complex numbers equal to 5, right? It's just a syntax error, okay? So, but what we can do, there's a simple fix for that. We can define this class p to the sharp p. Okay, so this is all the decision problems that you could solve in polynomial time if you had an oracle for solving sharp p problems. Okay. So this is sort of like the decision problem cousin of sharp p, and we can then see where does this fit in with the other classes. Okay, well it's not hard to see that p to the sharp p is contained in p space. It's good for the same reason that NP is, right? If you have polynomial memory, you can just keep looping over all possible solutions to your problem and just keep a running count of how many of the solutions are good. Right, that will take exponential time, but you can keep reusing the same memory over and over as you keep this count. Okay, so that will simulate each sharp p query within polynomial space. Okay, so we certainly have this, and we certainly have that, as I said before, if you could do sharp p, then you could solve NP complete problems. Okay, in fact, something much more surprising than this is also true. So. Toda in 1991 proved the theorem that the entire polynomial hierarchy is contained in p to the sharp p. Okay. In fact, with just a single call to the sharp p oracle. Okay. So you can reduce any level of this entire polynomial hierarchy to a counting problem. Okay, to just solving some one counting problem. Okay. So again, that is not at all. It shouldn't be intuitively obvious. If it's obvious to you, then come talk to me, okay? But counting is somehow astonishingly powerful, right? Captures the entire polynomial hierarchy. Yeah.
Is anything known about the number of isomorphisms in graph isomorphisms?
Oh, that's an excellent question. I think that that is not known or believed to be sharp p complete. Again, because the set of automorphisms is going to be a group, and so again it has this group structure that and that's going to be a very strong obstruction to it being sharp p complete, I believe. I could talk more about it offline if you want, but yeah.
Is there an interesting analog of counting hierarchy?
There absolutely is. It's called the counting hierarchy. So you can have sharp P with a sharp P oracle, sharp P with a sharp P oracle with a sharp P oracle, and so forth. And then that gives you a whole hierarchy of stuff, which is then all contained in P space. And yeah.
Just a basic question. So
Yeah.
the Sharpie oracle just outputs a number that
It
counts
does.
the number of solutions,
That's
or does it
correct.
enumerate the solutions?
Well, okay, it can't actually give you a listing of the solutions because there may be exponentially many of them, right? So it doesn't, there's not even the space to write down all the solutions, right? What it does is it gives you a count. It gives you a count of the number of solutions.
But
Okay.
then it seems a bit surprising that just by an extra integer, you could, enhance your P to the sharp P oracle to include all of polynomial hierarchy, because it seems like the information that you have is just one more number.
It is surprising, yes. So to be clear, right? The sharp P, the question that you're going to be asking your sharp P oracle in this simulation, right, is like a very bizarre question, which is derived in some way from your original pH problem, but which in some sense looks nothing like it, right? You're going to contrive a problem that such that by counting the solutions of this weird other problem, you find out the answer to your pH problem. Okay, it's a very clever reduction. Okay, so just a couple other, and I'm not just throwing out random things that are cool. I mean, they are cool, but I'm actually, as you'll see, all these things are actually going to be used, and in the arguments we're going to make about quantum optics. Okay, so a couple other things that are worth knowing. Oh, okay. Let me. Okay, so when we talked about the extended Church-Turing thesis yesterday, someone asked, a very good question. Are we allowing probabilistic computers, right? And at the time we weren't, but let's do so now. Okay, so in real life, of course, we often want to use algorithms that have access to a random number source, or at least something that we assume or imagine to be a random number source. Okay, we do that all the time when we're doing Monte Carlo simulation. For example, of course, randomness plays a central role in cryptography. You don't want to generate your key deterministically. Okay, so of course, we would like to know, what is the class of all efficiently solvable problems if we allow for randomness. Okay, and so that gives a generalization of P, which is called BPP. This stands for bounded error probabilistic polynomial time. Okay. If you like, this is just the class of all feasible problems for randomized algorithms. Okay, and so, but now the way that we define it is actually we have to be a little careful. So I'll show you. So we say that BPP is the class of all the languages, all the sets of strings, for which there exists a polynomial time Turing machine, M, such that for every input x, okay, now here's what we're going to say. If x is in L, then okay, so M is going to take two inputs. It's going to take, X, which is its input, and it's also going to take just a string of purely random bits. Okay, it's going to take a string of polynomial length, which we call R. Okay, and we'll just assume this to be a string of perfectly random bits. Okay, and now our requirement is that if for every input X, which is in L, M has to accept for at least a 2/3 fraction of all R's. Okay, for every X which is not in L, M has to accept for at most a 1/3 fraction of all R's. Okay, so a few points to make here. The first is that the x, the input itself, is not random in this definition. Okay, so we're still requiring algorithms that succeed, for every input, for a worst case, input x. Okay, the only thing that's random here is this auxiliary random string r. Okay, that but you can imagine that we get to pick r, maybe using a quantum mechanical random number source, maybe just using the last digit of the Dow Jones Industrial Average, or anything in nature that looks like it should be random enough for us. Okay, so now why do we put this this 2/3 and 1/3, right? Is there anything magical about these constants 2/3 and 1/3 here? Well, what we need about them is simply that they're in between 0 and 1, and that this one is greater than this one. Okay, so you can check that any here's another exercise if I didn't give enough. Okay, any choice of such constants would give rise to the same complexity class, BPP. Okay, yeah. No, absolutely not. No, these just seem like the two simplest numbers that are between 0 and 1 and different from each other. Okay, and that's why that's why they're adopted as a convention. One could also use 1 over pi and 1 over e. Okay, so yeah. Okay, good. So R is a string of some fixed polynomial length. Okay, so R is an element of 0, 1 to the p of n, where p is some polynomial. Okay, good. So R is the randomness that the algorithm uses. Okay, so now so we're appealing here to a very, very important fact about randomized algorithms, which is so obvious that it's sometimes like not even mentioned explicitly. But anytime you have a randomized algorithm, you can always think about it, if you like, as just a deterministic algorithm that takes some random bits as an additional input. All right, why? Because, well, anytime the algorithm wants to make a random choice, it can simply consult like the next bit in that random string in order to decide which choice to make. Okay, and conversely, if you had a randomized algorithm, right, you could, write a, take, conversely, if you had an algorithm that used such a string, then, you could simulate it by a randomized algorithm that just guessed the string randomly. Okay, so in other words, we're saying you can always pull the randomness out of a randomized algorithm, right? You can always just say the randomness was generated up front, right? It's just, it was a hidden variable, if you like, right? It was just, generated at the beginning of time, and then we just consult this, random string whenever we need to make a random choice. Okay, the analogous thing will not be true for quantum algorithms, right? We don't know any notion of pulling the quantumness out of a quantum algorithm, right, and just putting it, into an input. Maybe measurement-based quantum computing, gets sort of close to that, but not really. Okay, so this is really a special property of classical randomized algorithms, and it's going to be the source of a lot of the differences that are of most interest to us between quantum algorithms and just classical probabilistic ones. Okay, so all right, so that's another point to make about this definition. And then the third point is, why do we need this gap between these two numbers, right? Why couldn't we just say, look, if x is an L, you should accept with probability greater than a half, and if x is not an L, then you should accept with probability less than a half. Okay, well, in fact, we could have said that. And in fact, if we did, that would lead to another complexity class. That one is called PP. So it's like BPP without the P. BPP without the B. And PP will also be of interest to us later. I put on the homework to prove that PP is actually, although it's a class of decision problems, it is already, essentially as powerful as sharp P. If you have P with a PP oracle, that's, that lets you do sharp P. Okay, so the bottom line here is that if we didn't have this gap between acceptance and rejection, then everything would be too brittle, right? Then you could say deciding whether a randomized algorithm accepts with probability slightly more than a half or slightly less than a half is just too hard of a problem. Okay, or equivalently, right? If you had an algorithm that did that, that algorithm is not really directly useful to you, okay? Because how many times would you have to repeat the algorithm before you got any decent estimate of, whether X was in L or it wasn't, okay? So, the nice thing about having a gap is that now, let's say that, you're not satisfied with just being 2/3 certain of the answer. Let's say that you want to be 99.9999999% certain. Okay, in that case, all you've got to do is just run your randomized algorithm over and over, right? Just keep running it, but with different R's, okay, with different random strings. Okay, and then just take the majority vote among the answers. And then just standard, binomial theorem will tell you that your probability of making a mistake will decrease exponentially with the number of repetitions. And, if you just make 1,000 repetitions, then the chance of an error will be much smaller than, let's say, the chance that an asteroid will just come through the roof and destroy your computer. Okay, so as soon as you have, any kind of gap between these two cases, then you can amplify that gap by repetition. Okay, and then, you can get arbitrarily certain of the right answer. And this is why, we like randomized algorithms. Sorry, was there a question back there before? No, okay. Sorry, you had a question? Yeah.
If we accepted with probability 1, when
Yeah.
X belongs to the language, would it change the class?
Yes, then we would get a class called, which one? RP, okay? And then we could also say that you have to accept with probability 0 if X is not an L. No, sorry. If we say accept with probability 0 if X is not an L, and accept with probability at least a half if X is in L, then we get RP. The opposite, where we say accept with probability 1 if X is in L, and reject with some decent probability if X is not in L, that gives us co-RP. So RP and co-RP are both contained in BPP. I wasn't going to get into them. Okay, I was trying to minimize the number of classes that I have to expose you to. But since you asked, yeah.
You have to assume that the distribution for R is sufficiently uniform.
Yeah. So in fact, here we've simply assumed that it's exactly uniform. Okay. So here the assumption, as I said before, maybe I should have said it again, is that R is just a uniformly random string. Okay. Now there's been a lot of research about what if R is not completely random? What if it just has a little bit of entropy in it, right? And there's actually a huge amount that's known about that. It's known that, for example, if you have two independent sources of randomness, and each one just has a little bit of a tiny bit of randomness, then you can extract, like highly purified randomness from that. Okay, and then you can get bits, that are just like as close to random, as close to uniform as you like. So then you can do BPP. Okay, likewise, if you have like a very, very noisy, not very good randomness source, but you also have just a few bits that are truly random, then that's good enough also. Okay, so you can ask a lot of questions about given partial sources of randomness in nature, can you still do BPP, right? And there's been a lot of work on that, but for now we're just assuming perfect randomness. Yeah.
So you said that the numbers 2/3 and 1/3, only one needed to be bigger than the other.
Yeah.
What if both of them are less than half?
That's still fine because now so now it won't be a majority vote, but let's say that one was 0.4 and the other one was 0.2. Okay, then if you wanted to become very certain of the answer, all you would have to do is run your algorithm 10,000 times, let's say, and then ask, okay, did more than 30% of the runs accept? Right, and that will distinguish very well between the less than 20% and the more than 40% case. Right. Okay. So the point is, as soon as there's a gap, right, then you can just use the binomial theorem. Right. It doesn't matter where it is really. Okay. So. Okay, so what can we say about this BPP? Okay, so and we could say that sort of if we want to really modernize the extended Church-Turing thesis, right, then at the least it should say anything you can efficiently compute in nature can be simulated in BPP, right? We should allow, it seems fair to allow, a randomized Turing machine. Okay, as we'll see, that might not even make any difference, if we allow that or not. But, but you could say that the modern form of the ECT would, which is still probably falsified, but, it would allow for randomized algorithms in our simulation of nature. Okay, so what we know is P is certainly contained in BPP. You can always just ignore the randomness if you don't like it. Easy to see that BPP is contained in PP certainly, which is contained in P to the sharp P. Right? Intuitively, if you can count the number of solutions to any problem, then just count how many R's are there that cause M to accept, and then see is it greater than this fraction or is it less than that fraction. Right? So this certainly holds. Okay. In fact, once again, something less obvious is known. Okay, so you might ask, what is the relationship between BPP and NP? Right? And, well, we don't know in either direction. So this is not known, right? Because, how would you give, a short witness proving an answer to a BPP question is yes. What would the witness be? You could say, here are a bunch of random strings that cause the machine to accept. Okay, but that would be like a politician saying, look, I filled this entire room with people who agree with me. Clearly, most of the public agrees with me, right? It's just, it's not a proof, right? So this we don't know. But on the other hand, we do know there is a theorem from the early 80s due to Sipser, Gatch, and Laudeman, which says that BPP is contained in NP to the NP. So BPP is contained in the polynomial hierarchy, in fact, in the second level of it. Okay, and this is, again, it's proved in a graduate course. It's not even that hard. It's, I could do it in one lecture, let's say, but I don't have one lecture. Okay, so okay, in the other direction, you could ask, okay, can NP-complete problems at least, be efficiently solved by a randomized algorithm? Right? Is NP contained in BPP? This we also don't know. However, we would certainly guess that the answer is no. Right? I mean, this would have the same sort of intuitive consequences as if P equaled NP, essentially. And we can prove, so it is known, that if NP were even contained in BPP, then the polynomial hierarchy would collapse to its second level. Okay, so this is, yet another example of where, of this style of argument that, such and such is unlikely because if it happened, then the polynomial hierarchy collapses. Okay, so, right, so. Okay, so I guess the stage is now set for BQP, which is quantum polynomial time. Okay, and so Stephen already mentioned it yesterday, but of course this is a central object of interest to us in quantum computing, and intuitively this is just going to be the class of all the feasibly solvable problems for a quantum computer. Okay, so. So let me just define this and then talk about P, BPP, and BQP and what we believe about the three of them. So now with BQP, we have to we again have to think carefully about how to define it. So the original way that it was defined by Bernstein and Vazirani in 1993 was using a notion of a quantum Turing machine. Okay, so they just They took like David Deutsch's notion, actually, of a quantum Turing machine. They said just let the tape head be in a superposition of different, positions on the tape. Let the contents of the tape also be in superposition. In fact, let the two be entangled with each other. Right? Let the transitions that the tape makes be unitary transformations. Okay? This thing is a mess to define. Okay? And it's a mess to reason about. And so in sort of modern quantum computing research, what we almost always do is we just reason about quantum circuits, okay, which Stephen helpfully talked about yesterday. So we just reason about these, now the difference between a circuit and a Turing machine from computer science point of view is this. Okay, with a circuit, you have to specify in advance the size of the input that you're dealing with, right? So you could design a circuit for, let's say, factoring of 100-digit numbers, okay? But even if you did that, then for factoring of 200-digit numbers, you would need to design a completely different circuit, potentially, right? It's, a circuit is just a collection of gates just operating on some fixed, set of input bits, right? And so you have to specify in advance how many bits are we dealing with. Okay, a Turing machine, the whole cool thing about it is that you just design one machine which is then able to handle inputs of an arbitrary length. In particular, it could handle inputs that are much larger than itself. Okay, like many of you have probably used your LaTeX compiler to compile like a PhD thesis that may have been longer than the LaTeX compiler itself. Okay, so I'm not sure, but depends how long your thesis was. Okay, so. Okay, but now we want to. So if you have a single algorithm that works for any size of input, that's called a uniform algorithm, right? Otherwise, it's non-uniform. Okay, so we want to define BQP using quantum circuits, but we want to do so in a uniform way. And so the trick that's used for this is that you say, look, you need to start with a classical Turing machine, okay, and then that classical Turing machine will output a description of the quantum circuit to be applied. Okay. So we say BQP is going to be the class of all languages for which there exists a polynomial time, classical Turing machine, M, such that for every input x, M outputs a description of a quantum circuit C sub x. Okay, so like a circuit involving Hadamard and Toffoli gates, let's say, as Stephen talked about yesterday. Okay, such that so now this quantum circuit, will either accept or reject, right? So it'll be a circuit that you apply to, let's say, to some given polynomial number of qubits, which all start out, let's say, in the 0 state, and we can C0, we can Hadamard, we can Toffoli, and so forth. Okay, and then at the end, say we'll measure a single designated qubit in the 0-1 basis. And if we get a 1, then we'll say, okay, that's a yes answer. If we'll get a 0, we'll say that's a no answer. Okay, so now what we're going to say is that if x is in L, then C sub x should accept with probability greater than or equal to 2/3. And if x is not in L, then C sub x accepts with probability at most 1/3. Okay, and this is, for exactly the same reasons as we did this for BPP. Okay, that we didn't just need a gap between these two numbers, and then if we don't like that gap, then we can simply amplify it by running our quantum algorithm over and over, and then taking a majority vote, exactly as we would do in the classical case. Yeah.
You can also have deterministic quantum algorithms.
You can, yeah. That gives you a class called EQP, exact quantum polynomial time. Okay, but even the definition of EQP depends on exactly which gates are we allowing. So it's in many ways it's a less natural class. So I'm not going to talk about it. Okay. Absolutely, yes. So you could say, and this is sort of the evidence, so we have a lot of evidence that this is an extremely robust class. In particular, no matter how you try to define a quantum model of computation, whether it's using quantum Turing machines, quantum circuits, adiabatic quantum computing, measurement-based quantum computing, topological quantum computing, all of them, give rise to the same class BQP. Okay, so this increases our confidence that we've really sort of picked out the right notion here. Just like, for people to be confident in the original Church-Turing thesis, they had to see that all these different ways of defining a computer were equivalent to each other. Right, the same thing here. Okay, so all right, so what can we say? So certainly BQP contains BPP, right? Stephen already went through the argument for that yesterday, right? If you have a quantum computer, certainly at least you can simulate a classical computer. In fact, with this definition, well, it's trivial that at least you can do P. You could just completely ignore the quantum part and just use your classical control system to do all the work for you, okay? Which, when people make claims about, that they've built a quantum computer that can do such and such, this is always a question one has to ask, right? How much was the quantum part really doing, and how much was the classical control, doing? Okay, so okay, you can certainly simulate a classical probabilistic algorithm if you wanted. Now, what about in the other direction? What is BQP contained in? Okay, well, it's not hard to see that certainly we can simulate quantum polynomial time in classical exponential time. Okay, why is that? Well, because at the very worst, you could just have your classical computer store a complete description of the entire wave function. Okay, and then just update that gigantic list of amplitudes whenever any unitary transformation is applied. Okay, that will be hugely inefficient both in time and in memory, right? But it'll work. Okay, so in particular, this already tells us that quantum computers cannot solve uncomputable problems, right? There's no hope of using a quantum computer to solve the halting problem, for example. Okay, because the most you could hope for is merely, quote unquote, to get an exponential advantage over what a classical computer can do. Okay, and that's what we're saying here. Okay, but in fact, stronger things are true. It's not hard to see that BQP is contained in P space. So you can get a simulation, a classical simulation of any quantum circuit that, while it still takes exponential time, at least uses polynomial memory. Okay, and for a physicist, I can basically explain how the proof of that works with one phrase. It's because of the Feynman path integral. Okay, so instead of storing the whole, the entire wave function, which is like a wasteful way to do things, what you'll do is you'll just compute each amplitude of interest to you, and you'll compute each amplitude as a sum over an exponential number of contributions. Okay, contributions from sort of every possible path that you could take, sort of through the classical configurations, right? And each path will add some complex number to your total amplitude. So your amplitude, say alpha sub x, which will be like the final amplitude of the basis state x, will be the sum over a whole bunch of y's, let's say, of alpha sub xy, with each one of these computable in classical polynomial time. Okay, and then the final thing you're interested in will be a sum over all x that that correspond to the machine accepting of the absolute value of alpha sub x squared. Okay, you'll then be interested in, is that thing greater than 2/3 or less than 1/3, right? Because this is the final probability that your machine will output yes. Okay, so the problem just reduces to the computation of this sort of quantity. And this can certainly be done in polynomial space, albeit exponential time. Okay, and in fact, if you think about it a little bit more, you can even do this simulation in P using a sharp P oracle. Okay, this gives you BQP and P to the sharp P, which was also observed by Bernstein and Vazirani. And then if you think about it a little more, and this is on your problem set, you can even show that BQP is contained in PP. Okay, this was, when I first got into this field like 15 years ago, I was very excited when I proved this, and then I discovered that it had been done a year ago. So this is due to Adelman, Demarest, and Huang. Okay, but Felt like, okay, at least I'm, instead of doing 100-year-old stuff, now I'm merely doing 1-year-old stuff. But so, okay, so this is where, this is a rough picture of where BQP fits in. Now, the relationship between BQP and NP is not known. Okay, so but we don't know containment in either direction. So I think today almost all of us believe that NP is probably not contained in BQP, right? That to have a polynomial time quantum algorithm for solving the NP-complete problems just seems like a really tall order. Okay, and I could go into the reasons for that later. Okay, but there's also an interesting question of, is BQP contained in NP? Okay, so this would say, when a quantum computer produces a particular output, is there at least a short classical proof that it does that? Okay, and this is also not known. And I would say that we don't even have any really compelling example of a problem that should be in BQP but not be in NP. Okay, at least if you're talking about like languages, if you're talking about yes or no, conventional yes or no decision problems, then we really don't have good evidence either way on this question. Okay, now part of the point of this series is we're going to see later that if you broaden what you mean by a computational problem, to encompass, let's say, sampling problems or search problems, then we can give very compelling examples of problems that are solvable in quantum polynomial time, but that don't have NP witnesses, and in fact that are not even in the polynomial hierarchy. Okay, so one could also ask, is BQP contained in the polynomial hierarchy? Unlike with BPP, this is not known. Okay, this is another open problem. But again, part of what I'm going to try to do with linear optics is show you examples of at least sampling problems. So not technically in BQP, okay, but sampling tasks that can be done by a quantum computer, but that cannot be done even with an oracle for pH, unless pH were to collapse. Yeah.
You said that BQP is in BQP, so if
Yeah.
BQP is in NP, so again the hierarchy collapsed to the second level.
Yeah, you're right. If BQP is, you're absolutely right. If BQP is in NP, then certainly BPP. Well, wait. But if BPP is in NP, then that doesn't say anything about the hierarchy collapsing, though. If NP is in BPP, then the hierarchy collapses. Okay. So this is this is basically what we know. And so now let me just end by telling you what we conjecture. Okay, about so we can ask P, BPP, and BQP. This gives us a very nice sequence, like deterministic algorithms, probabilistic ones, and quantum ones, right? And do we get more powerful algorithms as we go further in the sequence? So here are the modern conjectures. I would say, first of all, this surprises many people, but it is overwhelmingly believed today that in fact P equals BPP. Okay, it's believed that any classical randomized algorithm can be de-randomized with only a polynomial increase in its running time. Okay, now why do we believe this today? Because this would follow as long as there existed good enough pseudo-random number generators. Okay, so as long as you had like for any randomized algorithm, as long as you had a way of just deterministically generating numbers to feed to it that are sort of as good as random, right? Or that algorithm will not be able to tell from truly random numbers, then that's enough, right? This is all you would need. Okay, so, and of course this is what we do in, in actual programming, right? When you call like the rand function in your favorite programming language, to get a random number, really just doing some simple linear congruential, it's doing something deterministic, right? Which might be seeded originally by some
What about the seed then?
Yeah, that's right.
You can't have a seed.
That's right. So what you, okay, so here by a good pseudo-random generator, what I mean is a generator that can start with a seed with only O of log n bits. Okay, so it has to be able to start with a truly random seed of logarithmic size, and then expand that to a polynomial size string, that this algorithm cannot distinguish from that the target algorithm cannot distinguish from true randomness. Okay, and once you have that, then you're good to go, because then you can simply loop over all possible strings of log n bits. That there are only polynomially many different such seeds, so you can just try them all. Okay, and then you get an estimate of your algorithm's acceptance probability for a truly random string. Okay, now what was discovered about 15 years ago by a bunch of people, especially like Nissan, Vigderson, actually, people who were here at Hebrew University at the time, is that like under very, very generic assumptions in complexity theory, like that a problem that should obviously require exponential size circuits does require such circuits. These good enough pseudo-random number generators would exist. Okay, so it's known under very, very plausible assumptions how to get pseudo-random generators that would be good enough to imply P equals BPP.
Good enough in this case mean that you can't distinguish them from pseudo-random
Yes.
polynomial time?
Yes. It means that you can't distinguish, at least for any fixed polynomial running time. Like you would have to first pick the polynomial, like n to the fifth. And then you would design pseudo-random numbers that are like this, and that no n to the fifth algorithm can distinguish from truly random. Maybe an n to the sixth algorithm can do so, but So okay, so there are today a few problems that we only know how to solve in BPP and not in P. Okay, quadratic residuosity is one example, right? And there's a few others where we have very clever randomized methods, but no deterministic one is known. As I mentioned yesterday, the primality problem for a long time was known to be in BPP, and now we know that it's in P. Okay, so you could view that this is a successful empirical prediction of the P equals BPP hypothesis. Okay, by the way, this prediction was also made by the Riemann hypothesis, by the extended Riemann hypothesis. Okay, it also predicted that. So this is a successful prediction for both of those conjectures. Okay, yeah.
So I sometimes see when people talk about efficiently simulating a quantum algorithm
Yeah.
classically,
Yeah.
they say that if the quantum system is always in a matrix product state with
Yeah.
some fixed bound dimension,
Yeah.
then it's classically efficiently
Yeah.
simulated.
Yeah.
So do you know if that class of like all problems that where the quantum system is always in a matrix product state, is that equal to BPP or something?
Well, I mean, so look, it's certainly going to be contained in BPP by the result that you just said, right? Or contained in P. It's going to depend on the details of how you define it, whether you get all of P or all of BPP or something a little less than that. Okay? Because, so like you have to know, can you at least can you encode a universal classical computation into this problem? That'll depend on the exact definition of the problem. Okay? But, so anyway, so let me end with the conjecture that in contrast to the classical case, most of us believe today that BQP really does give you something larger. Okay, that quantum polynomial time, really is bigger. Of course, the most famous piece of evidence for that is Shor's factoring algorithm. Okay, so Shor showed in 1994 that factoring, the decision version of factoring is in BQP, which means that if P were equal to BQP, let's say, then factoring would have to be in P. Okay, so that raises the stakes, right? That because if factoring, as we said, is almost certainly not an NP-complete problem, but again, we do use it as the basis of modern cryptography. Okay, but now the same sort of special structure that factoring has that prevents it from being NP-complete and that lets us use it as the basis for modern cryptography, the same sort of special structure was exploited by Shor in order to find a quantum algorithm for factoring. Okay, so just to draw a picture, so our conjectured world map would be P equals BPP, and then above it is NP. At the top of NP are the NP-complete problems. Above NP-complete is plenty of other stuff. And then here's BQP. And BQP snags some more of NP than P does, like the factoring problem. It might even snag some stuff that's not even in NP at all. We're not sure about that. Okay, but probably not all the way up to the NP complete problems. Okay, so it looks like all the problems today for which we know efficient quantum algorithms are really quite special, right? Either factoring, discrete log, they all have some sort of special properties that seem to prevent them from being NP complete. Okay, so really, this intermediate zone is sort of the target for most quantum algorithms research. Okay, so now there's so we might say, okay, so then as long as we believe factoring is hard, then quantum computing overthrows the extended charge Turing thesis. Okay, and this thesis we might as well bury it, put a fork in it, it's dead. Okay, well there are a couple problems, right? One is that quantum computers haven't been built yet. There are a few people who think that they could never be built. I don't agree with them, but but there's that. It would be nice to actually demonstrate this experimentally. Second problem is that factoring, we're not, we're really not all that confident that it's not in P, right? There are a number of theorists who think, yeah, it probably is in P. Maybe the NSA even knows how to do it in P. Okay, although if they did know, then it would seem weird that they have to, strong arm all these companies into giving them backdoors and stuff, right? But so can we get sort of more safer evidence, more generic evidence that BQP is really larger than P? Can we even get evidence that could be demonstrated using simpler quantum systems, and thereby give both like an easier and a sort of more secure route to falsifying the extended charge Turing thesis? That's what I'll talk about tomorrow. Thanks. Yeah.